So I just got a fantastic task. So I got the task of, of introducing today's speaker. So I'm going to say a few words of your view, if that's okay. Yes. Professor Jianhua is the chair professor of mechanics and leader of the Geotechnical unit at the Hong Kong Polytechnic University. You received your PhD from the University of Manitoba in Canada in 1990. I mean, there is a few people in this room that maybe were not born then yet. So Professor Jin has a good track record in research and has played a leading role in the development of advanced soil testing equipment, innovative fiber optic sensors, establishing a large multi-scale purpose physical modeling facility for studying geohazards. So I really hope that you have visited the lab already. Yes, perfect. I hope that you have enjoyed that and got to see as well. So Professor Jin has received the extensive honors in geotechnical engineering. I mean, not all of them are listed here, but I read them in the meeting invitation. It was a lot of them. So you were ranked in top 88 among more than 50,000 scientists in geological and geomatics engineering in the world's top 2 in Stanford University. It's a fantastic tip. So it's a great pleasure to have you here. I know that this is one of the series of presentations that have been happening this week. I was unfortunately sick in the first two, but I'm really looking forward to this.
Thank you very much for your introduction. It's my great honor to be here. Okay, you get my thing, please. It's really a great honor here. And I mentioned just a story 2 days ago, some link with the NGI. Okay, from my early work and from my previous supervisor with the link NGI. So it's a great honor. And today's my talk is we focus on numerical methods and the simple methods for consolidation analysis of clay soils. Okay, and I delivered this talk in March this year to the Canadian Geotechnical Society as fourth distinguished lecture in the CGS. And why I give this lecture, because just the end of last year, my 2 methods are adopted by the Canadian Foundation Engineering Manual, basically included in the Chapter 7 related to sediment definition. And this Chapter 7 was written by Dr. Ben Ferenis. Okay, he retired, but he is responsible for Chapter 7. I try to convince the 2 chief editors to accept my 2 methods to be included. After communications, they accept my 2 methods, which will be adopted in the manual. It's not easy, but I'm lucky. Okay, my 2 methods are adopted, but for other manuals, maybe take more time to do so. And you can see 2 subsections. 2 subsections. One is fully coupled methods, simple methods. In the subsections are in the manual. I don't go details. This is the reason I want to deliver this talk in Canadian Geotechnical Society. This is basically repeating of this lecture. Okay, you can see the contents of my talk: introduction, hypothesis A, hypothesis B, and what's the fully coupled methods, simple methods, and the general one, conclusion remarks. The number 1 is all the consolidation problem of saturated soils are related to effective stress. The definition of effective stress, I don't want to repeat. I know you know quite well in this area. Effective stress is very important in soil mechanics, especially for saturated soils. Okay, I don't want to overemphasize. I just mentioned a little bit is recently we developed a special fiber optical sensor-based transducers. We can measure effective stress directly. It's a new invention. Okay, that's I will not discuss here. And the Tasaki peg, follows. And the one-dimensional problem, the simple method is basically for one-dimensional problem. 2 or 3-dimensional methods are 3-dimensional problem. Okay, I don't want to repeat. And I showed this one another day already. And some slides I will skip very quickly. Okay, to save more time later. And the consolidation problem actually is a coupling of the soil skeleton. Very important is a coupling of soil skeleton. We can use spring to represent the soil skeleton, they have water in the voids. Basically, the coupling of the two components, skeleton and water, no air. Okay, this is for saturated soils. Okay, so any compression on the surface, okay, the water will come out. There's a spring. That means the skeleton of soil is compressed. It's a coupling process. And of course, for soil, the behavior is non-linear and is also height dependent. So this spring for soil is very, very complicated. It's more complicated than the elastic spring because the skeleton of the soil is elastic, viscoplastic, and non-linear. So that's this is just a symbol to show you the coupling. The spring for soil is far more complicated. And the sediment top pizza is a good example. I don't want to say too much. And the sediments of two artificial islands is also a good example. I mentioned another day. Hope you listened to my talk in Quebec City before. And I go very quickly. For engineering design, very important is the control post-construction sediment. What's the meaning of post-construction sediment? When the foundation is done, I don't want more sediment to occur after the construction of foundation or building or facilities. Okay, this is really important for geotechnical design. Anything occurred before this one, no problem. Even we want the sediment to occur as quickly as possible, so that the post-construction sediment is small as possible. The problem is, how do you know the sediment before? How do you know sediment afterwards? We need a method. That's important, okay? So we need a good understanding the sediment deformation of the soils and how to calculate or predict the sediment for the whole life, okay, of the structures from beginning to the end. And this figure I'll show you another day. For one artificial island one in Kansai International Airport, people calculated or people predict the sediment is the yellow one, up to 2030, no more than 6 meters. It's just I don't know what method they use, but the calculation is wrong. Okay, but the real measured sediment is much bigger. Go to 9 meters, 9.1 meters, even bigger. But the predicted one sediment only 6 meters. A big difference. This means something wrong with the calculation method. I believe the laboratory data in Japan is reliable because the Japanese are doing the test very careful. Nothing to do with the laboratory data, but I think the calculation method is the issue. So we put a question mark here. I guess they use the hypothesis A method. Okay, that means hypothesis A methods doesn't consider creep or visco compression in the primary consolidation. That's a big issue. They even invite Professor Messery to Japan to give some advice to them. And also Professor Norwegian also invited by the Japanese expert, but no people in Japan invited me. I tell you, I'm doing the better work, really. Really, I tell you the truth. And later, I have some interactions with the Professor Watabe. He was in charge of the port works. He was the senior researchers in the Kansai Port Works Research Institute. And at one time, he also considered hypothesis A is right, hypothesis B also right. He published a paper based on his laboratory tests. He said my data support A, also support B. But I don't believe that. So later, my students, including your students, the DACO, okay, spent many years studying the laboratory data. And the conclusion is the data published, including the data provided by the Japanese people, actually they do not support hypothesis A. Actually, they all support hypothesis B. And my students recently did a lot of work in this area, also support all the data by the Japanese people, provided by Japanese people, support B, not A. I will discuss more later. So this is Watabe, okay, Dr. Watabe, Professor Watabe not convinced by us. So we write a joint paper together. The paper will be published in Geotechnical very soon, probably will appear this year. Actually, he's convinced. Before he said A is right, B is right, okay? So I want to tell you something wrong with the method. So this is one way to compensate the big compression by jacking this up. I think this is not a good solution. You have no choice. Okay. So the second runway, the first runway, second runway. Second runway is they waited for longer time to surcharge the soils. So for the runway 2, they surcharge the ground longer time. So need more sediment occur. Need more sediment occur before construction. So finally, this construction, post-construction sediment is smaller. They wait for a longer time. Need the sediment to settle. They're getting more stable, then start to construct the runways. This is a good choice. So they learned a lesson from the construction of first runway. Okay. Hong Kong sediment is also a big issue. I skip this one. The creep I mentioned before, another day is a phenomena. Phenomena is for example, for odometer test, we apply a load, keep it constant, then we can observe the compression develop with time. Lasts for a long time, maybe 5 years, 10 years, even more. Of course, getting stable, no failure, because odometer test is a confined test. Okay, no failure. Okay, so finally stable. Why we have this kind of creep? I think depending on the materials. Okay, for plastic materials can also have a creep, but a plastic is a one-phase material. But the soil we have two phases. Okay, one is skeleton and water, so it's different material. So mechanism which cause this kind of viscosity of the soils is mainly due to the physical chemical reaction, okay, of the particles and the water. Because the water molecular has two poles. Okay, one is the positive pole, one is the negative pole. The clay surface carry negative electrical charge, so it's attracted on the surface of clay surface, which cannot move that freely. Okay, fairly. So this may lead to this one. This is on the surface, on the particle level, then on the skeleton level, they which have this kind of viscous behavior. Okay, I don't go details. So how do we know the viscosity? How big is the viscosity of soils? How do we know how big is or small? And the one simple test we all know that is the odometer test. Okay, we do odometer test on the one stage of loading and keep constant. When you compress soil sample, we measure the vertical compression. For vertical compression, we can convert it to the voice ratio. So voice ratio can decrease gradually, and this is in the local scale. And at this turning point, okay, the excess population is nearly zero. In this period, excess population is bigger than zero, and we call this period is a primary consolidation period. And this period afterwards is what we call secondary compression period. Okay, in the secondary compression period, because the excess pressure is zero, so that the vertical effect stress is constant. Vertical effect is constant. But in this period, because the excess pressure is more than zero, so that the total stress is constant. But effect stress is increasing with time. Okay, effect stress increasing with time. So people will argue, say, oh, the soil will have a creep only after the primary consolidation, only afterwards, because it's very clear, easy to understand. Because the compression here, the vertical effect stress is constant. So on the constant vertical effect stress, we can see continual compression. Oh, it's easy to understand. But in this period, effect stress is increasing with the time. It's not constant. So people say, oh, it's complicated. No creep in this period. You know, in reality, that's not true. So that this slope in the secondary compression period, normally in A method, okay, A method only start from here. But the B method, this line can be extended back, but also maybe not a straight line because the effect stress is changing, increasing with time. But in any way, this period, the soil skeleton also has the viscous compression. We don't say the creep because the effect stress is changing, but we have viscous accumulated viscous compression in this period. So this is a big difference. No visco or visco. We consider visco compression, no visco compression. So we have two hypotheses. One is A, is the old one. One is B, is the later one. That's the idea. Another one is the slope. Is a good indication the viscosity of the soils. Okay, C alpha E defined in terms of voice ratio. and the longer time, okay, increment, with ratio longer time. If the flat, that means C alpha is small. That means viscosity is small. If it's very sharp, very steep, then the C alpha is bigger, viscosity is bigger. It's a good parameter to indicate the viscosity of the soils. And C alpha E defined in voice ratio. Sometimes people confuse. I prefer put alpha E and also put alpha epsilon. C alpha epsilon is defined in terms of strength, compression strength. But C alpha E, C alpha epsilon are linked to each other by 1 plus E naught. That E naught is the initial voice ratio. And in the odometer test, I also want to say is the standard duration is 24 hours in the laboratory. We run the test on each increment node for 24 hours. Okay, then we plot compression curve. Of course, you can do the test longer time. Like Professor Hans Peter do the test 22 days. You discuss your paper today. If you want to see very clearly the trend of the secondary compression, you can run longer time. Longer time, you can see the trend better. 1 day not enough. 7 days probably the minimum. Want to see the compression clearly. And even longer time is better, but it's time consuming. Okay, time consuming. And for very, very long time, and Professor Hans Peter found another method to the unloading. Okay, to get the long-term quick behavior faster, rather than wait for the quick test for a long time. To the unloading to the same point, you can get the C alpha E also. Okay, to save more time. That's another approach. Okay, this is what I want to show you. This diagram can give us another information about the viscosity of the soils. Now, C alpha E for different clays around the world, including Norwegian plastic clay. I found the Norwegian plastic clay is very similar to Hong Kong American clay. The range of C alpha E very similar, not very significant. Okay, this is what we have done for Hong Kong American clay. I don't know the details, and also see for Hong Kong American clay, and the behavior can be straight line. If the stress is very, very big, can be getting the slope is getting smaller and smaller. It's not linear, and also creep. The creep, you can see here narrow. This is bigger. The line. It's not really in parallel. Okay, you behavior. So I propose a nonlinear function to feed this kind of creep behavior. I show you Professor Hans Peter this morning to feed this kind of nonlinear behavior. A nonlinear function, which is very useful. Okay, very useful. I don't know the details. Now, what is A method? What is B method? Okay, here I discuss this issue in more time. Okay, last talk I mentioned a little bit. I didn't go into the depth, but today I'll go into the depth, discuss what's A method and B method. Okay, A method. If you based on A method, okay, assumption, the equation can be equal to this one. Okay, say for one layer of the soils, and first one we have primary consolidation. In sediment, we need to just up to here, up to here, up to here. Okay, the voice ratio decreased. That means the compression. Compression is related to sediment. So this part is from here up to here. So for the time, this is 0. Bigger or equal to 0 to TEOP in the field up to here. This EOP means this one, the end of primary consolidation. Okay, EOP means this. Okay, that means at this point, excess pressure is about 0. The excess pressure here is bigger than 0. So for this period, okay, here the primary consolidation is equal to UV as final. UV is the average degree of consolidation, which is related to hydronic flow, hydronic seepage of the soils. Basically, follow Darcy's law. According to permeability, Darcy's law, the water come out from the voids on the hydraulic gradient. Okay, of course, dissipation is dependent on the permeability. It basically related to permeability, which follow Darcy's law. H final is basically the compression up to this point. Compression up to this point may be including elastic and plastic. Maybe including elastic viscoplastic part up to this point. Anyway, up to this point. And okay, and in this period, no creep, no visco compression in this period. Okay, this is the main equations. And you can get this curve from laboratory. I mentioned before, in laboratory, this is TOP, normally only a few minutes. We can do the creep test for 24 hours. So go beyond here, up to here, 24 hours. Okay, say 24 hours up to here. But actually, the TOP is only a few minutes. I believe for Norwegian clay, or a few minutes. Okay, not very long. But if we run the test, do the creep test more than a few minutes to 24 hours. But in the field, this equation is applied for the foundation in the field condition. In the field condition, the thickness of soil samples can be a few meters. You know, in laboratory, okay, the thickness of the specimen only 20 millimeter, right? So this time is only a few minutes. But in the field, can be a few meters, say 2 meters, 4 meters, 8 meters, even 20 meters. So that this TOP in the field can be much, much longer. Can be a few years, can be 50 years, even can be 100 years. Depends the thickness, depends on the permeability. So if we want to apply this equation for the field condition, this TOP must be cover field to calculate the end of primary consolidation for the field condition. This one for laboratory doesn't apply. It applies to a wrong condition. Field is much bigger. So if this for the field condition can be 10 years, 50 years, that means for this period, no creep. This is a big issue. A method, assume here, no creep. Okay, the B methods, no, that's wrong. This is wrong. We have to consider creep. That's the argument between A method and B method. Now, not finished yet. A method for this period, that means this period, no creep, 0, no creep. But after this, they add atom here, atom here. This is the C alpha E, the slope. 1 part E naught. This is related to strain. This is a type dependency. This is the thickness of soil sample. Then this is a quick compression. Is this compression here, up to here, the compression here, depending on the time. Start from here, compression. So consider quick. And this actually, after this point, actually UV is about 1. Is about 1. So actually is final. This is about 1. Then have a secondary compression. This is A method. And another argument is, of course, is the end of primary consolidation. If we want to determine this point at UE equals 0, mathematically, I can tell you the time should be infinity. In reality, that means no creep in the infinity period of time. But fortunately, the engineers, okay, consider end of primary consolidation when UE or the average degree of consolidation maybe 95% or 98%, not 100%, okay? Maybe 95, 98%, then we can back calculate TOP, okay? We go this way, okay? In mathematical point of view, you want to UE equal 0, UV should be 100%. That means no creep at all in the whole life, okay? Maybe many of the year, no creep, okay? That's not correct. So engineers make some correction on this one, okay? But still need the assumption of this one, okay? So in conclusion, hypothesis A method is incorrect because the creep visco sediment in the primary consolidation is not included, okay? And this method normally on the estimated sediment. That's why Kansai International Airport, people calculate the sediment much smaller than the measured one. This can be at least be the main reason. One main reason, maybe some other reason, I don't know, one main reason. So this method is wrong. And also I will show you, including Professor Hans Peter's students, the Gardner published a paper, they also show a method it actually is logically, scientifically is wrong. I will show you the argument. I show you 2 arguments, okay? Prove a method is wrong. I will show you later, okay? And you can see how to define the hypothesis A, hypothesis B, and you can go back to a paper by not 1977. And you can see here. And A methods are proved, which is correct, which is wrong. One simple explanation is this one. According to A methods, okay, for the thin specimen, for the thin, For example, in a laboratory, only 20 millimeter, you can get this curve. Turning point is here. So this point is the end of primary consolidation. According to A methods, for the thick sample, say for 1 meter or 2 meter, for example, thick, then come back to here. The turning point is the same. A method, okay? That means you know what's the meaning of this for different thickness. You can see the strain. You keep in mind, these two curves is on the same stress, strain. This is a time. So this point, nothing to do with the time. You can see the horizontal. That means with time, no link, no correlation. Is horizontal. So that according to A methods or curve A methods, the strain, the stress is independent on the time because nothing is a flag, independent with the time, right? For different thin sample or thick sample, even thicker up to here is also horizontal. That means the stress, effect stress, strain relationship for this point and the end of primary consolidation is independent of the time. That's one conclusion we can draw, right? Number one, then you can see another contradiction. But after this turning point, the strain on the same stress is depend on the time. This is the increase with time. So after this one, the strain behavior is depending on the time. You can see depend on the time. Not only for thin sample, also for the thick sample. You see according to curve A, also increase with time. That means after the primary consolidation, the end of primary consolidation, the strain behavior is depend on the time. This is a clear contradiction. You can see for the same soil skeleton, the soil skeleton is the same, but in this period, I mean for this period, the strain behavior is the time independent. The same soil skeleton after this point, then the time dependent. How can we have this kind of material in the world, in the reality, in the physical world? This behavior for this period is time dependent. After this one is the time. Before this one is the time independent. After this period is time dependent. It's a really artificial division. It's not in the earth. We don't have this kind of material. It's a contradiction. It's impossible. Right? We develop a constitutive model, like a soil equivalent model in practice, which can be applied for soil skeleton in the primary consolidation and also afterwards, because it's for the same soil skeleton. Doesn't matter which period. As long as the same soil skeleton can be applied. But here is a contradiction. In this period, not elastic plastic. Of this one, the elastic viscoplastic suddenly jump to the time dependency. It's a clear contradiction. Okay, this is one argument. I don't want to repeat, okay? But B method is come back here. So this turning point is a B method turning point, B, before and afterwards all depend on the time. It's consistent, scientifically it's consistent. That's the B method, okay? So I want to go to detail. This is one contradiction. Okay, another one is go back a little bit, not here. Okay. We have another contradiction. Another contradiction is when the soil layers. Okay, when at the beginning after apply loading, now the boundary. If this boundary is the drainage site, then that boundary will have effect stress increased to nearly to the maximum immediately. So as this boundary layers will have a creep immediately. But overall, average default consolidation is much smaller than 50 or 60. Okay, so that's another contradiction. I don't want to go to details. We can find another contradiction of A method. Okay, I don't go to that details. Let's skip this one. This is aside Dr. Dagog's work. Okay, and Professor Hans Peter was his co-supervisor. He told me, okay, he visited Hong Kong last year, so I invited him to give a talk. He also demonstrated, he approved And A method is wrong. See, it's horizontal here, nothing to do with the time. But afterwards, this A method here, afterwards, after this one is a time dependent. Before this one, time independent. Is scientifically wrong. It's wrong. It's not consistent. Okay, but B method no problem. B method, okay, it comes to here. Increase this point increase with time, inside or outside, before and afterwards. Okay, this is the big difference. A assumption, B assumptions. Okay, A methods. Okay, this curve in the primary consolidation is in laboratory in the field is nothing to do with the time. Okay, for any time is the same curve. Okay, but in reality is different. Okay, in reality is different. So it's clearly contradiction in the method. I don't recall details. Oh, this is another explanation of the contradiction in the A method. I mentioned before is when you suddenly apply a load, then have it start the drainage at boundary condition. For example, just apply load. If this boundary conditions, then effect stress at the boundary will become a constant immediately. But the poor pressure dissipation not come to zero yet. But if this is a drainage boundary, the effect just increase to the constant immediately, then we have creep. Starting from here. But the average default concentration is smaller than 100%. So we have creep here already. This is the inside of primary concentration period. So this is another argument which say the A method logically is wrong, assumption is wrong. Okay, there are many. And also, I mentioned Professor Watabe. Okay, he originally supported hypothesis A. He was a senior scientist in the Port Works Research Institute in Japan. He worked there before. He believed his data support A and support B. But later, including Dr. Dagago, he also studied the data, including his data. Actually, this data, he interprets the data in the wrong way. Okay, in the wrong way. If you interpret the data in the correct way, actually all the data support B, not A. And finally, he is convinced by us. Okay, he changed his view. Okay, his data actually support B. So we have a joint paper will appear in the Geotechnic this year. Okay, I don't go details. So go back to the two methods. Okay, I don't read all this, included in chapter 7. Before I introduce that simple methods, okay, two methods. One is the fully coupled methods. Fully coupled methods actually you know already. People don't say this is a method. People don't say this is a B method. Actually, you know this already. B method, fully coupled methods actually is this fully coupled consolidation analysis. Okay, basically based on the continuous porous continuum. Okay, mechanics. Okay. First one, we assume the soil is fully saturated. Okay, it's not for unsaturated soil, for saturated soil. We know this one. Okay. Second one, the soils are a porous continuum because all finite elements, continuum mechanics is based on assumption. These two basic assumptions. Then we have other 5 equations. Consider elements of the soil elements. Consider stress equilibrium. Consider strength displacement relation. And consider effect stress equation. Then we need a proper constitutive equation. For soil skeleton, we need an elastic viscous pressure model or the soft soil equilibrium model. The soft soil equilibrium model, in fact, is an elastic viscous pressure model. Okay, we call this a nonlinear rheological model. Then we need Darcy's law because of the coupling water flow. The water flow due to different hydrologic gradient follows the Darcy's law. This one is the follow nonlinear viscous flow law. This is also time dependent. Is related to viscosity of soils. This is time dependent, depending on the seepage of the soil and the soil skeleton. Two are time dependent, but from different mechanisms. Okay, we need to find equations to solve together. Then the B method. We call this I give this a name. This is the rigorous one because in this approach we don't need any stupid assumptions. What I say stupid assumption is what's the period primary consolidation, what's the period secondary compression? We have the separate the two period, right? In this approach we don't need. The separation of primary consolidation, secondary compression is a stupid assumption because we have no better choice. In early days, in 1950s, 1960s, the computer was they didn't have a computer, even no good numerical methods. So they have to make assumptions. Okay. Nowadays we have very powerful computer. We have a reliable numerical methods. We also have very good elastic viscous boundary models. We solve all together by computer. Is a hypothesis B. So in practice, you know practice, with the soft soil equivalent model, do the consolidation analysis, the sentiment you got is hypothesis B method already. You know so already. So this is what I want to say. Okay. Okay, I'll give you all the equations, 5 equations. Okay, everything here. I don't go details. This is for constant model. Don't use linear elastic model. Use the elastic with capacity model or soft soil equivalent model. They can solve together. Okay, you can get this is hypothesis B approach. Okay, I mentioned another day. Okay, the soft soil equivalent model. You know, in practice, and my model are very similar. Okay, I don't go details. For one-dimensional case, we need a one-dimensional constant model. Again, 5 equations are same, but a constant model a little bit different. This is a one-dimensional elastic EVP, one-dimensional elastic with capacity model by Yin and Graham. We combine together to solve it. Then solution is based on hypothesis B. It's a rigorous hypothesis B. We don't have to make any stupid assumption. Oh, this is a primary, this is secondary compression. No need to divide this period. The solution is automatic, cover everything from beginning to the end. Okay, so I don't want to go details. Oh, by the way, and my PPT files and example files and paper files, you can get those from Dr. Lee or get from Professor Hans Peter. I save you the files in your computer today. If everyone you want to know the files, okay, PPT, example files, papers, you can get it from Dr. Lee. Okay, the two gentlemen. Okay, so easy. You know this already. Oh, another interesting story I will mention. I believe in this world, the strongest supporter of hypothesis A is still measuring. He's still measuring, and his students, he's still alive, and his students also believe his approach is correct, including some people in Hong Kong in the government. Okay, I had some trouble. I had some trouble to include my method in the foundation manual in Hong Kong because one of his students had a strong view against my approach. So in this world, we still have some people who have old minds, wrong views. They still want to keep it. I hope the people today listen to my talk. Actually, Professor Dan Hansen, he believes hypothesis B already. No need for me to convince you. Okay. For other people, you have an opportunity. Listen to my talk. I hope you can convince. I hope you will be convinced today. And you will convince other people to accept hypothesis B. I tell you very frankly. So I believe the strongest supporter of hypothesis A is still Misery and his students. And some people support the hypothesis B too. I mentioned before, one Japanese professor, Watabe. Another a big guy, a very famous guy is Andrew Vito. He's also a big guy. He's the head of the Department of Civil Engineering, MIT. MIT is a big university, and he did a PhD in Imperial College. But I believe nowadays people in Imperial College also support hypothesis B. Hypothesis B. No, they will not support hypothesis A. I don't say he's wrong. I don't say he's wrong because he published a paper, Vito, paper. He has published an EVP model we call no isopac mode. He said his model in the paper can support A, also support B. You know why? Because some test data published by Watabe, some data also support A and support B. I guess he probably want to make sure his model is universal. Oh, my model can support A and support B. Or it's better than other models. You know what I mean? You know, he's a big name. Oh, I can say my model can cover A and cover B, so better than your model. Your model only support A or B, but he can support both. I don't believe this because I had a meeting with him in Hong Kong, and also his student. Fortunately, his student was working in Hong Kong, so we had a long argument discussion with his student. I had one meeting with Vito in the office in Hong Kong. In the meeting, he still insists his model support A and B, but because he's a big name, right? He gave a Tasaki lecture this year, and he's a big name. I don't want to argue with him in front of my students or his students. I'll say, okay, I will do the work first. I want to convince you. So later, Dr. Yuan was working in Hong Kong. So my students had meetings, discussion with him for at least half a year. And we analyzed all the data, test data. I mentioned before, right? Dr. Wadabi, he said his data support A and support B. Similar to Dagago, okay? I want to reanalyze the data in a correct way. Okay, that's one work we did. Another one, we re-studied this paper. I studied this model. My students spent all the time to study his model. His model very strange model, very strange. Okay, not the conventional one. Spent a long time studying his model. Finally, we got a conclusion. In this paper, in order to, I don't say them, in order to show his model can support A and B, actually we found out, in order to support A, he artificially changed some parameter. Artificially, to reduce some values of parameter in order to feed the data happens A. It's wrong. It's wrong. You cannot say for one source, you cannot change the value of parameter. Should it be the same source, right? For the same parameter, you can artificially change some parameter. My student found out, and he's convinced. He said, "Oh, indeed, I changed the value." So it's not scientific way. So finally, we study this model. It's a good model. It's a more complicated model. Support hypothesis B only. No, you can artificially change the value, right? But I have no time to convince him yet. But he's in Hong Kong. He needs more time. He's a more senior guy. Okay, need more time. I will send the paper if it's published. Okay, the paper in this area will be published very soon in Geotechnical. When the papers come out, I will send him the paper. Okay, so what I want to say is the truth only one. You can only, for one fact, you have two truths, right? The truth, scientific solution, the truth only one. So I don't believe the data can support A and support B. The model support and support B. If something is wrong there. So we, after a lot of work, including Professor Hans Peter's work, Dagado's work, okay, test data, I actually support B, not A. It's wrong. And also regarding the models, we also find out only support B. If the model is correct, only support B, not B and A. You know what I mean? So I don't go into details. It's some story I want to mention today. This for one-dimensional case, the fully coupled method for one-dimensional case, we use this elastic viscoplastic model for one-dimensional case, solve all equations together, then we can get the rigorous hypothesis B solution. I don't go details. Or the proof, I don't go details. That means one-dimensional case, one-dimensional strain, consolidation case, fully coupled methods. We solved this one in 1996. A publication in Geotechnical. I don't go details. This is a comparison of prediction and test data. I don't go details. Okay, I don't go details. And some people use my model in Japan and also get very good results. This is for the peat. This in Chinese is the peat. Peat is the behavior is highly viscous. Okay, you can see if a Tasaki solution, because Tasaki solution is the best assumption. Soil skeleton is elastic. Is elastic. So no creep considered. So hypothesis A means to at the end of primary condensation we add a slope. Okay, that's the second compression. So we have a method here. Initial solution is by Tasaki, then followed by compression. That's a prediction. But real data is shown here. So Japanese professor consider my model fit data much better because my model consider viscosity and elastic viscoplastic together the inside. Okay, you can see the papers. And Professor Nash applied my model, and a professor in Bristol applied my model for the field condition. Okay, my proof, my verification was based on laboratory data. I believe he was first one to use my model for the field sediment predictions. And he also found my model fit the field data so well. Okay. I don't want to go details. fully coupled methods for one-dimensional case, 2 or 3-dimensional case is good. Of course, you need a computer software, like processor, you need the knowledge. You have to choose software equivalent model in practice, all right? You need some experience to do so. Engineers, probably for them, they have some difficulty. Okay, so that's the problem. Okay, for you people, for it may be not is okay, but for engineer, it's very difficult. Okay, so I was thinking to have a simple method which can have a good is accurate enough for engineers to use. I tell you, I had this idea 20 years ago. Only my idea was realized just a few years ago, or 3 or 4 years ago. Finally, I come out a simple method, and which can be done by hand calculation or by spreadsheet calculations. So this is what I call the simple method. Okay, here. So everything's good. Fully coupled methods, difficult to use. The simple method is here. That's the second part. My methods in the manual. Simple method is here. Just adding here. See, in the primary consolidation period. So you have quick. This one the same as before. This one is after. From the time is more than this one. Just this item. U is the average degree of consolidation. You can get the U from the textbook for the chart for some solutions. Okay, very easy. S final can also you can calculate it easily, similar to hypothesis A method. The difference here is the creep. This creep and final I will discuss a little bit later. What go to details is impossible today. I need 3 hours at least. Okay, today 1.5 hours. I want to leave more time for your discussion, so I don't want to waste your time. And you want to understand this method more, you can get my PPT papers from Professor Hans Peter, and everything here can be derived by hand based on our concept understanding. So my simple equation method is not the empirical one. It's based on my theory, based on the equivalent time concept. Okay, alpha beta is a little bit empirical. I will show you the reason why alpha beta is empirical. But this division actually is very good. And how to calculate S creep? S creep final is something new here. Okay, this is the simple equations, not differential equation. Okay, no differential equation. So everything can be done by hand or by spreadsheet program. And all the parameters can be related to conventional parameters. Okay, like CCR is related to recompression or the compression index in the over consolidation area. CC is a compression index in a normal consolidation compression period. P is a pre-consolidation pressure. Okay, you can get the sigma P from the odometer test. And C alpha here in my equation, it means C alpha E, defined in terms of voice ratio. This is very commonly used by engineers. T0 I choose 1 day because we can get the compression curve from the data with duration 1 day, already. So T0 1 day. Okay. E0 is the initial voice ratio depending on the initial water content of the source. Alpha, beta are 2 empirical equations. Why we can show why we say 0.8, 0.3, because based on back fitting with more reliable solutions from practice. I mean, practice is I mentioned before, is a rigorous numerical methods. So we do the calculation, use the practice, then use a simple method to match. So alpha, beta basically is 0.8, 0.3. Maybe we'll vary a little bit. You can try. Maybe 0.7, maybe 0.25. Maybe it's also okay. The difference is not very big. Okay, but these 2 parameters, if you try my method, you can play around. Okay, so it's not a big issue. K is a basic property of the hydraulic conductivity of soils. One thing I want to point out when you read my paper, one thing is very tricky. Is this one. Do you know this one? I should probability. I made it before. When you determine U, I said you can get a value U from the textbook or from some analytical solutions. Then you will ask me, what's the assumption those chart analytical solutions are best to get a U? I tell you,
U is based on assumption the soil skeleton is elastic. You know, Tasaki consolidation theory, you can determine U, the soil skeleton is elastic. That's U. So this U is based on analytic solution, assuming the soil skeleton is elastic. But in reality, the soil is not elastic. But in my method, we still use U. It seems to me a little contradiction. But how to solve this contradiction, I want to point out. If you read the papers, probably you don't know how the difference. You can see, in reality, for example, compression here to here to 4, increase a lot so big. From here to here, turning point, the behavior is nonlinear. To get ace final, they're nonlinear. But when you determine the U, we need to assume the behavior is not elastic. In my equation, my simple method can consider nonlinear behavior, and unknown behavior is okay, it's nonlinear. But when you determine U, you have to assume the behavior is elastic. How to solve this contradiction? I tell you one small tips is here. This delta epsilon from here to here, you can determine delta epsilon, the incremental strength, consider nonlinear behavior. Okay, so this delta epsilon consider nonlinear behavior already. This stress increase, no change. Then this MV is back calculated. This is a trick. This is back calculated. When you determine U, you need MV. So MV come to here. K is the permeability, we know it. The unit weight of water is a constant. MV is from here, is calculated. Okay, then you can determine CV, the degree of consolidation. When you CV, you can get the U. So simple methods can consider nonlinear behavior. At the same time, we can get the U based on assumption the behavior is elastic. Actually, if we draw a diagram, we determine the sigma, it becomes nonlinear. When we determine MV, consider a second from here, consider not here. So we consider both already. So no contradiction in my method, okay? That's all the same. My simplified methods can consider consolidation in the normal consolidation period, even unloading, reloading, even in the over consolidation period. I tell you, my simple method can calculate the settlement for all the situation. Very important is only use the same C alpha E. Okay, in my simplified method, C alpha E is from here, consolidation here. I mean consolidation in the normal from the normal consolidation line. The C alpha E is from quick test from the normal consolidation state. But the same alpha E can be used through my equation, my method here, also for unloading, reloading, even over consolidation point. All can be used. I don't go details. Today is impossible for me to go into details. Okay, so all those parameters in my simple methods can do all complicated calculations. Unloading, reloading, over consolidation, everything can be done. And here show you how to derive all the equations in my slides. So you better to get my PPT, okay, to see all the steps. All the steps, all items can be derived here. There's a concept. And also including what's the equivalent time, and I read Professor Han Peter's paper. You also see equations, how to get the equivalent time, actually here. Impossible for me to go to details. How to determine equivalent time, for example, what the corresponding equivalent time at the point 2. If we know the stress, we know strength, then we can get this TOP. Because in simplified methods, we need to know the equivalent time. Okay, I don't go to details. Okay, impossible for me. But if you read my PPT, my papers very carefully, you can see all the items can be derived, not empirical, not the trial and error. Okay, it's empirical. It's derived very rigorously. Okay, I don't go details. Then some example. Examples, and also you can get my Excel file for all the examples. Okay, in reality, okay, for example, for a very simple case, even soil is uniform. On the vertical chart, soil is uniform. Okay, And the initial stress maybe is linear. Because the all behavior is non-linear, okay? So we have to consider initial the effect stress. So you can see initial is not constant. So even you have to consider this increasing of initial effect stress. How to consider it? Of course, one simple way is to consider one layer to be a single layer. Use the middle point. You see middle comment here. Consider that to be average initial effect stress. Consider the whole layer to be a single layer. Then my calculation is here. I don't want to repeat. Okay, that's not good enough. Not good enough. Okay, you can see all the results. I did calculation for A method, B methods, all here. All can be done by hand. Okay, I don't go details. Okay, all calculated by hand. Okay, you can see I skipped all the details. A method, then on the estimated settlement. Okay, A method. B method is better. Is more. Is correct. This is for OCR equal to 1. Normally consolidated case. This is for OCR equal to 1.5. If I remember, this is an over consolidated case. I don't go details. Now, more accurate results. Okay, I go back there. More accurate result is divided in sublayers. Sublayers, because this is sigma v, sigma I is increasing with time. To get more accurate results, it be divided by even 2 layers, and 4 layers, the more. Okay, I have done some calculations. Okay, divided into 1, 2, 4, or 8 layers. They get more reliable results. You can see this is increasing with time. In some cases, we have multiple layers of soils. You still have to divide into different layers. So divide the soil into different layers is a very simple way to solve the non-homogeneous situation. Okay, this is to show you. For the simple case, the sigma I is increasing with time, with depth. Okay, this is 1 layer, 2 layer, 4 layers. This is 8 layers. Then you can divide into more layers is more accurate. Okay, including MV. Do you remember MV is back calculated, right? I mentioned before. You can see when the layer increase, it's getting constant, 8 layers. So for very different with thick layers, or for the multiple layers divided into sub layers, you can get a very reliable result. I have done all this. Okay, you can see. Okay, hypothesis A on the estimated settlement. Hypothesis B method here. The dot, circular, triangular are from Praxis or from Consol. Consol is a numerical program written by my former students. Okay, this is a weakness method, and use alpha 0.8, 0.3 is better to fit this area. For here, no big change. Okay, this one basically affect the behavior in this area. Okay, so use this one can fit the data in this area better, more close to use the circle, the triangular, more fit the data from rigorous numerical methods better. That's why I say alpha, beta are a little bit fitting parameters. You can play around. Okay, play around. So this is a comparison. More. Okay, I don't go details. And also for multiple layers, the same idea can be applied for the 2-layer case. I don't go into details. For the 2-layer case, I don't go to, again, compare with Praxis. Okay, you know Praxis very well. I don't go details. And water drain also can be included. The water drain, if a water drain, as long as uniformly the settlement is uniformly settled down, then you can just use the average digital consolidation, consider vertical consolidation, vertical consolidation. You put in my simplified method. Everything works very well. Another very interesting analytical solution, because in my simplified methods, I need you, right? In my simplified methods. We found another very interesting analytical solution from Walker in Sonata. This based on this equation, they can get the average digital consolidation for any layers, multiple layers. Actually, if you want to know the analytical solution, you can use this Excel file. Okay, based on this solution, you can get this Excel file from me if you want. Okay, my student. This. What I mean is multiple layers, and we have vertical train. This is vertical train. We have smear zone, any loading, and my general simple method is for this one for multiple layers. But you still have to have UJ for each layers. UJ for each layer. How to get UJ for each layers? Okay, you need an analytical solution. And fortunately, the solution for Walker Enchilada can provide to us. Okay, fortunately, okay, we tried it. It's good. Almost finished. Okay, we published a book. Okay, and you can get some solutions, in this book. And also, we published a paper for general case. I don't go details. I need more time for question. Okay, sorry. And also, we verify this general simple methods for multi-layer case based on the data from Hong Kong, case documented in Hong Kong. Oh, conclusions. Okay, this I want to emphasize again. A method is only one is wrong. 100% is wrong. Okay, and I can underestimate consolidation settlement. Okay, this underestimation is on the risk side. Risk. Okay, risk, not on the safe side. Okay, risk is bad. And the rigorous hypothesis method is the fully coupled methods based on the differential equation. So fast sets of differential equations, but you need a computer program and knowledge. Simplified B methods I've introduced very briefly today. You can do this by hand or by spreadsheet calculations. And it's quite accurate. Okay. We propose another more general one for multi-layers, vertical train, multiple loading. Okay. You need more time to study. Okay. Now a little bit more complicated, but still can be done by hand calculations. Settlement from the new simple methods are in good agreement with the fully coupled method. Okay. With fully coupled methods. That means simplified method is quite accurate. Okay. It's simple to use. And 4 papers. You can get 4 papers from Dr. Ray or Professor Hans Peter. And my Excel files, for examples 1 to 3, you can also get them from Dr. Ray and Professor Hans Peter. Okay. Thank you very much for your attention. Sorry, it's wrong over time.
Very impressive presentation. Thank you, Professor Lin. Any questions about this presentation?
Okay. This one. Gentlemen, no, lady first. Okay.
When you have hypothesis B method for calculating the settlement,
yeah,
is it affecting also calculating of settlement time based on contradictory of the thermodynamic theory of 1D consolidation theory? So like it seems like you predict a greater T90 or U90 consolidation, 90% or 98%. Is it a factor of the numbers you get it from the tables or calculate from the real time?
Okay, number 1, okay, hypothesis B methods, okay, is used to calculate the sediment of the source or the foundation or the structure of the source, okay, and can calculate sediment for the whole period from beginning to the end, including what I say the primary concentration period and after primary concentration period. So it can cover the whole period. And you mentioned the T90, T80 is not the main focus of the hypothesis B. It's not focus. And the hypothesis B methods, I also say one is the rigorous one, one is the simplified one. Rigorous one is just the best assume so is the porous continuum and solve the fast set of differential equations, you get it. But you have to how to solve it and use the conversion program. Simplified methods is based on same idea. The same idea means we have a visible compression in the primary concentration period and also visible compression afterwards. This is the basic idea is the same, but method is simple to use.
Usually I got asked about, say, right, I'm put on the preloading cell on a piece of land.
What do you mean preloading?
I like a load, heavier load on a piece of land to actually.
Okay, heavy load on a piece of land.
Yes. Okay. And like I need to advise like for the contractors how long this one is going to wait for a 90% of
for the 90% of the degree of concentration period.
So like okay. If I'm using hypothesis B, so like 90% of consolidations compared with hypothesis A seems a bit greater. And like for me, getting off a T90, I can only get from the table. It's a fixed number. Okay, I understand your meaning. Your question, meaning of your questions. Okay, if you put zero plus charge on the piece of land, and how long I have to wait until the concentration is nearly 95% or 98%. Okay, I use the A method to predict
This all use B method to predict this one. The first one, I tell you, if you use A method to predict it, okay, it's wrong. Can give you a wrong results of when the soil can reach say 90% or 90%, 95% of average digger concentration. Give you a wrong answer. Okay, use a B, give you a better, more accurate solution. The two values from A method, B method will be different.
Yeah, my big T from the table is actually from based on A method. Right?
You are right. You're right. But you cannot use T90 from the chart. You cannot use T90 in the chart. You cannot use that. You have to use if you use simple method, use a simplified method, or use the proxies. Proxies to run the loading, and then what the pore pressure distribution. Then you can determine what's the average T1 concentration. Then you can use the proxies to run. You can determine T90.
Yeah.
Not T90 from the chart. The chart is based on assumption the soil behavior is elastic. You know what I mean? Yeah, hypothesis A is the first part of hypothesis A. Hypothesis A has two parts. One is for primary computation, one is for secondary computation. So that's don't use the chart. Okay, you run the proxies, or you can use my simplified method to do the calculation. Oh, by the way, when the soil behavior is non-linear, is especially elastic viscoplastic, the digger concentration definition can be defined in terms of pore pressure, can also be defined in terms of sediment. I tell you, the average digger concentration can be defined in different ways. If the soil behavior is non-linear, the two definitions give you two different results. If the soil behavior is elastic, then two definitions give you identical value. But unfortunately, again, soil is non-linear, so they will give you different answers. So it's best to use a proxy to run. Okay, or use the simplified method to do the calculation, give you a better result.
Is this the purest creep still considering or still happening?
You remove after remove.
Yes, after remove that, I'm hoping like on my
Okay.
my settlement is actually
Okay, you have to listen to Professor and Peter. He studied after unloading what's the creep. After unloading what's the creep. The creep is smaller, but it's still creep a little bit, depending how much you unloaded.
Does it have the memory of the first?
Oh yeah, memory use the first.
It has the first influence when the loading of the preload.
Yes.
Okay.
The previous loading will have some influence on the behavior of the loading. If you are loading too much, then creep is getting smaller or even zero. But you are loading a little bit, it's still creep is very big. I read your paper. Okay.
And we need to continue with questions, otherwise we use all the time. Kjell, you have some questions, and then we see a lot of questions also from the.
Well, then the gentleman first. Okay.
Yeah.
You're asking me later of the meeting.
My name is Kjell Carter, and I've been working with settlements since my master's thesis at MIT in 1969. And so, and we've had a lot of discussions with Hans Peter about the modeling.
Okay.
One question to you is that you're using the C as a constant parameter.
CC. Okay.
If you go CC, yes.
Agree.
But if you look at the modulus concept of Jianhua, and we have worked with, and I worked with what we call the block sample database, which shows that CC is far from a constant parameter, and you have to use the modulus concept to properly define the compressibility of soil clays. Otherwise, you really miss important aspects of the soil behavior, and that would also impact how you deal with the creep problem. So you need to go into the modulus concept and the creep parameters that are defined in relation to the modulus concept, rather than using the old C assumed constant value.
I fully agree. With you. And also we discussed this morning, Professor and Peter. So CC is not a constant. CC will decrease with the water stress. If you see the figure published by Dr. Beren in 1967, you can see the trend non-linear. So I fully agree. Fortunately, I have done some work in this area already. I proposed a non-linear function to feed this kind of non-linear compression already. Today, I have introduced this function to Professor and Peter already. And based on that non-linear function, I have also derived the elastic viscoplastic model already, and also put it into simplified methods as well. So my revised updated methods can consider this nonlinear compression behavior, and also including creep. Creep will not occur, will not increase indefinitely with time, will end at a certain point. It's also nonlinear. I mean, C alpha E. I mean, C alpha E is also nonlinear with time.
It follows that everything is not as linear as you think it is, right?
You're right.
So,
You're right.
so it's important that if you're going to have any kind of fully reliable method, we have to take care of the nonlinearity or the compressibility even in the normalist consolidated rate, so to speak. Yes.
I fully agree with you. So I have done some preliminary work in this area already.
Good.
And so you can look into my papers. Okay.
Good.
Thank you very much. Cool questions. Okay, very good. Okay.
Who did you check who I am next door?
Yeah. Who last time he asked you a question, but he didn't have the opportunity. Yeah.
Okay. Ask me. Okay.
Yeah, okay. Thank you very much for your very interesting presentations. So I have a question related to the creep effects under varying loading conditions. In your example, you show your presentation, you show 2 examples. I think one is the Kansai Airport and the other one is Pizza Tower. And we see that there's significant long-term settlement was observed. So I'm wondering, how does your model account for type of time varying load, like seasonal fluctuation or repeated traffic loads?
Okay. Okay. First one. The first one is the time dependency. One is related to density load. Okay. One is related to viscosity of soil skeleton. Okay. If for a good methods, a good model, we should consider both. Okay. In my presentation today, you also refer to Pisa Tower settlement and also Kansai International Airport settlement. If you use my methods, okay, should give you better prediction of the settlement of the Kansai International Airport. Okay, give you better prediction. But the Kansai International Airport is a little bit more complicated than just a simple one-dimensional case. Okay, so I can say, because it's also have to consider 2 or 3-dimensional effects. Something which I haven't considered yet. Because you can see this is artificial island, okay? It's not a perfect one-dimensional compression. You know what I mean? Maybe a little bit 3-dimensional. So, and also multi-layers, and also creep consolidation. So for a comprehensive, a good simulation, prediction of settlement of Kansai International Airport, you have to consider also 2 or 3-dimensional effects. And multi-layers, the creep compression of the soils together. Okay, so you can try this one with the praxis. Praxis with solved soil model, which can 3-dimensional praxis model. You can simulate everything together. I mean before, praxis with the solved soil model is a hypothesis B. Is on all sides. Is that okay?
Maybe I can add a comment to it, because you talked about that you have varying load in time. And the way to solve that is that you don't use physical time. You need to always update your time each time you change your load or effective stresses. So it means that T is not starting from something. You don't use actually time as a parameter to control the creep. You use another parameter to control it. Therefore, you can always vary the loads continuously. It's not a problem, because you update your creep rate continuously.
Yeah. Okay, you can play around. Okay. Praxis with solved soil model is good model. Okay, no problem. My simplified one, you can compare the 2 for some typical problems. My simplified model for the moment is basically for 1-dimensional case. For sure, cannot solve 3-dimensional case. Okay, so you be careful. Okay, Eddie.
Thank you.
Samsung.
Yeah. Hello.
Oh,
Hey, Professor
finally I see you.
Yeah.
Finally I see you, okay, appear on the screen.
Yeah.
Okay.
Yeah.
Okay, any question, please?
Good to see you. Good to have you to see you in Norway disseminating this. So what I have is more of a comment than a question. I think education, like we discussed earlier, and dissemination, raising awareness is very important because many are glued to this hypothesis A type of thinking. But one thing is sample quality, which is very important. Yeah, which is very important in this discussion of hypothesis A and B. that hypothesis B needs high sample quality or representative sample quality, while hypothesis A has been using some disturbed parameters. And I think that will be good to emphasize with this simplified methods.
I fully agree with you. When you want to calculate the sediment or real case, you have first one have to get the high quality samples, okay, to get all the necessary parameters. So I fully agree with you. And when people do, I mentioned the example in Japan before. The data from Watabe say some data support A, some data support B. You did some analysis for all the data, but your conclusion actually all data supported B. Actually, this is one test. The results are very strange. Okay, it's very strange. We cannot simulate. You use data, one data is very strange. Okay, scattered quite far away. Finally, we contact Professor Watabe. He said, "Oh, that data may be something wrong with the test. Something wrong, not reliable." Finally, he asked us to skip it. So sometimes we give you the data for various reasons. The data not reliable. More important is when we compare A is correct or B correct, use the test data, make sure all the tests data are from the same soil samples. You cannot say compare to different soils with another soils, then put it together, because the comparison should be on the same soils. So the same quality soils, and also under the same initial condition. I remember your paper particularly point out, but some soil samples initial conditions are different, but you put it together comparison, because soil the behavior. Usually the point here or 2 point here or point here for the comparison is incorrect. You have to put the same initial conditions. So I fully agree with you. High quality sample is number one. Then some other factors we have to consider. Okay, thank you.
Yeah, yes.
Okay.
And the last one.
Last one.
Hi.
Hello.
Okay.
Thank you, Professor, for the presentation. I have a question about the issue related to the isotech method. Hypothesis B, especially about the initial phase of the loading. The issue is that the isotech predict a higher rate regarding the actual measurements in the ground in the initial phase of the loading. I want to have your thought on this, and in following this question, also second question is the unloading is also isotech, or especially the large amount.
Okay.
Yeah, thanks.
Okay, the isotech model, what's the meaning of the isotech model? Professor Hans Peter can give you a better explanation. My understanding is for the compression, the stress and the strain compression, isotech model means for one line, the quick strain rate is the same. Or for this line, okay, then we have polynomial lines with different strain rates. Okay, so that's the basic ideas. This viscoplastic strain rate in different lines, and the vertical strain and horizontal stress is dependent on the strain rates with different strain rates. Okay, so that's relationship is unique. That means initial loading, unloading. It is
but that is the assumption. And
assumption. Okay.
So that was the reason why we actually was doing tests for checking this. We was checking in a way what was the difference, what was the history effects of coming to different isolar and isotechs, whether we was creeping with constant stress and time, or whether we was unloading. So we was doing quite in a way. So we have a paper of that, investigating exactly this, whether this is a totally unique relationship that is independent of the history of how you reach this isotech.
Exactly,
So,
history, yes. Recently, MIT group also published a paper, a new viscoplastic model that connected isotech A to isotech B because of this issue. One of the issue was like, because the initial stress in the ground is over-consolidated somehow, and during the loading, isotech B produces higher strain rate because it quickly get to that unique ratio between the rate and loading. but isotech A is behind. So they introduce another factor, kind of like R. It just sounds to me ad hoc, but anyway, because it's related to the rate of the loading. This was kind of like, this is, I think, worth looking at, in my opinion. And another thing was about unloading, amount of unloading. Is it isotech? Like, for example, we unload the sample from like the consolidated state, large amount, relatively. Is it following the isotech method? I mean, there is a unique relation also there between rate.
For the unloading, of the unloading, the creep rate is smaller. It is smaller, even zero. So actually, if you see my screen, share the screen, you can see this item. I don't know how to, maybe you cannot see that. Okay, you can see my elastic visco plus model on the screen. The second part, okay, which is a viscoplastic strain rate, which is dependent on the strength and stress only. This strength stress can be in the normal concentration state, can be in the unloading reloading state. So this can show you, my model can show you, in the unloading reloading state, the visco strain rate is smaller. It's smaller, okay? So the model can handle this one, but this model still needs some improvement when the unloading is huge. Okay, that's another story. I don't want to say this one. So I believe isotech model can also work for unloading reloading case, but Professor Deng has Peter still consider this assumption needs some data to verify. But we want to see. So I consider isotech model still work for unloading reloading case. And I also want to point out the isotech model and my model is related to each other. It's almost the same. Final conclusion is almost the same. A little bit different in the parameter, but it's about the same. We support the same ideas, the same points, okay? But if you have time, you can look into my papers and my PPT, and you can play around to try. Okay, you can get my PPT from Dr. Ray. Okay, he's here. Or Professor Hans Peter. Get my PPT files and play around to see what's the behavior in unloading reloading case. Okay, you need
thank you. Thank you, Prof.
Okay.
Any questions?
Oh, people are gone. Okay. It's okay.
Yeah.
Okay.
Thank you for your presentation.
Okay. Thank you. Thank you.
Thank you very much. Bye bye.
Thank you. Thank you. Bye bye. Bye bye.
Thank you.
Bye bye.
That's better.
But then I have a problem. Because I have another meeting actually that I need to go to.
Okay.
But it's starting at 1 o'clock.
Okay. You go. I will communicate you by email.
Okay.
Further discuss on your papers.
Yeah.
Okay, I have a quick photo.
Okay.
Maybe we are all together.
Yeah.
Okay.
I'm nobody.
We give the evidence, the audience, come together. You